Hello. In the previous unit, we implemented STDP in excitatory synapses. You should have seen weights grow without bound due to the reinforcement of causal spiking. There is another important part to this picture. Until now, we have mostly implemented inputs with independently chosen spike times. But we know that neurons in the brain can receive inputs which are strongly or weakly correlated. So in this unit, we will implement a method for creating such correlations in spike times between inputs, based on a thinning of Poisson spike trains. It is taken from the work of Romain Brett, from this reference here. So in order to create the spike trains, we first take a Poisson spike train, as we have seen before, with the firing rate R source. We then copy these spikes with probability P independently for every spike, where P depends on the correlation C we wish to obtain between these new spike trains. Now, unless P is 1, you will of course obtain fewer spikes here than you had here, so the firing rate will decrease. In order to compensate for the loss of spikes, we take another Poisson spike train here with firing rate R noise, which depends on the target firing rate we wish to achieve, P and R source. In this case, we take the target firing rate to be the same as R source. We then simply add these spikes to our new spike train and obtain the final spike train, which in itself is still Poisson, but is now instantaneously correlated to the original source spike train. You can repeat this process for as many times you like, for all the spike trains you need. The cross covariance is shown here, depending on P again, firing rate, and a delta function centered at lag 0. So you can see from this delta function also that there are instantaneous correlations between these spike trains. In order to obtain broader correlations between spike trains, we can simply take these spikes and jitter them randomly after copying them. For more details, see the course text.